And lastly, I'm excited to introduce Rachel Skipper here at ENS, who will be talking about maximal subgroups of Thompson's groups.
Thanks. Everything I'm going to talk about today is joined with Jem Belt at Glasgow and Colin Blake and Martin Quick at St. Andrews. Great. Mateo gave such a nice introduction to the Thompson groups that it'll save me saying a few things here, or at least writing them down. But yeah, so right, these three groups, were introduced by Richard Thompson. So Thompson introduced these three groups, F, T, and D. Right, so we've heard all about these three groups already today. But historically, a lot of the reason people have studied F, T, and D, really, if you think about the questions people are asking, they're about the subgroup structure. So for instance, when Thompson introduced them, he introduced them as possible counterexamples to the von Neumann conjecture. So if you remember what the von Neumann conjecture says, it says that a group is non-amenable if and only if it contains a free subgroup, but this is false, we now know. But as Mateo mentioned, it's still completely open whether F is indeed amenable or not, but it was in fact an important theorem of Brin and Squire. In 85, where they showed that F has no free subgroups. On the other hand, one of our main reasons for studying T and D is that T and D gave first examples of finitely presented infinite simple groups. Which again is, a statement about the existence of normal subgroups, right? Like this is also a property of subgroups that we're talking about here. And so sort of a general motivating question maybe one can ask is what obstructions are there to a group embedding in a Thompson group? Right. Yeah, so really, this question maybe is a little harder for T and D because they have so many things that do really naturally embed in them. So for instance, as we've already seen, right, so the focus of today's talk will mostly be on D. And so I'll say that D has all finite, so every finite group embeds in D. Similarly, you can get free groups. So free groups embed in V for any size free group you want. Z to the n embeds in V, et cetera, et cetera. And in general, it's a hard question to say like what groups maybe don't embed in V. But it is the fact that there are groups that don't embed into V. So Blake and Salazar Diaz prove that, for instance, if you take the free product of Z squared with Z, that it will not embed into V. But beyond that, there's not so many things that we know that necessarily, are not going to embed into this group. On the other hand, though, because all three of these groups are finitely generated, it's sort of a general fact that we can prove kind of easily. Is that in every, so in a finitely generated group, every proper subgroup is contained in a maximal one. Proper subgroup is contained in the maximal one. And so, if you're trying to understand this question of what types of restrictions can occur, if you can get a sufficiently good understanding of your maximal subgroups, then you can possibly try and answer this question. On the other hand, another reason to care about maximal subgroups is that maximal subgroups correspond to primitive actions of the group. So recall, we say, right, a group action is primitive if it's not going to preserve any block structure. So primitive means does not preserve blocks, not preserve any non-trivial blocks. And so we often think about primitive actions as being the building blocks of group actions in general. These are, sort of our basic pieces. And, it's a fact that an action of a group G on some set X is primitive if and only if point stabilizers are maximal. So in other words, right, the way you can kind of think about this is whenever you have a primitive action, it's really the same as the group acting on some maximal subgroup by left multiplication or right multiplication. And so, right, so again, in these groups, they're very much defined in terms of their dynamics on spaces like Cantor sets, circles, the unit interval. And so, if you're trying to understand the various types of actions that this group can have, this is also maybe another starting point one can work with. Right, so sort of the motivating thing that made us start thinking about this question was questions about, does V have proper subgroups that have similar dynamics to V itself? And so we started trying to understand these maximal subgroups, and it turned out the answer is yes if you start looking at these things. And so these should be the things in the back of your mind as to why, one might be interested in understanding these. All right, so let's give a formal definition of V. So you've already seen somewhat of a definition, so Thompson group V. And I'll be giving, some similar definitions and some that are a little bit different than Mateo's Thompson group V, but things that should look reminiscent of what you heard in the last talk. So let's take an indexing set. So I'm going to look at binary trees, and I'm going to use 0 and 1 to index this tree. So my vertex set then is finite sequences in 0s and 1s, and of course the infinite sequences we'll write as X omega, and this gives us a tree structure, a rooted tree structure. And so, right, and so what we have is the vertex set here is this X star, the boundary of my tree is my X omega set, which again, we're going to generally be thinking about this as a Cantor set. All right, so to define V, let me define first what we call cones. So for some vertex in my tree, we'll define cone V to be a set of infinite sequences, so VW, where W is an X omega. So it's the set of infinite sequences beginning with V, and then, in our picture, our tree Right, if this is my vertex V, then the cone is, the portion of the boundary that's passing through this. And so then we can define certain maps on the Cantor set by taking partitions. So let V1 to VT and V1 to VT be two partitions into cones. Right, and then we can define a map, psi, from x omega to x omega, which takes anything that begins with ui and maps it to vi w. So all it's doing is it's taking a prefix off and replacing that prefix with one of our other prefixes. So we call this a prefix replacement map. And then V we define, so V is the set of all prefix replacement maps. Great, bad board work there. Right. And so alternatively, we can work with this tree pair diagram picture, as you saw in the last talk. So I'll do this by example. So second definition. Using strand diagrams. All right, this will be a definition by example. So let's take, for instance, the prefix replacement map that takes the cone 0 and maps it to 0, 1. The cone 1, 0 to 0, 0, and the cone 1, 1 to 1. So the way I'm going to draw this is I'm going to draw the two trees as you saw in the last talk, but instead I'm going to draw one of the trees upside down. So the first tree would be this. So my leaves here are 0, 1, 0, and 1, 1. For my codomain, I'm going to draw a similar tree, but upside down. So 0, 0, 0, 1, and 1 is the leaves. And then we just connect up the leaves corresponding to what the map is telling us. So it says 0 goes to 0, 1, so I draw a connector there. 1, 0 goes to 0, 0, I draw a connector there, and I draw a connector there. So when I draw these pictures, because I want to emphasize that these tree pairs, these strand diagrams, are not unique. So for instance, if I take this piece and I cut it in half and replace it with 1, 0 on the side and 1, 1 on the side. So what I've done is I've split these two cones into two halves, and I map the left half to the left half, the right half to the right half. And that represents the same element as a homeomorphism of the Cantor set. But on the tree here, it's going to correspond to putting an extra caret here and connecting the two sides, right? So this will be important for us as we start looking at these maximal subgroups to keep in mind that you can always kind of break things apart, and that this is sort of steadily going on in the background of everything we're doing. So yeah, we can define V alternatively here. If V is the set of all equivalence classes of strand diagram. All right, so what's happening here then, these two descriptions of Thompson through V, is they're giving, in addition to the action on the Cantor set, there's a partial action that's going on here as well. And what it's giving us is this partial action on the set of cones. So V has, so this defines for us a partial action of V on the cones. So for instance, any cone that's like on the interior of the tree here, it might not have a well-defined image, and so this is why we're only getting a partial action. So we have a, anything that's the leaf of the tree or outside of those, below those leaves, those all have well-defined images, exactly like this, for instance, right? The two children here have well-defined images, and their well-defined images are exactly the left and the right half here. And so you have this partial action, it's not a full action, right? Because there are vertices where the image is undefined. But so what we'll say here is we'll say, to define this action, so for alpha and beta, say finite sequences, so alpha, beta, and X star, we'll say alpha G equals beta if the cone at alpha maps to the cone at beta by G via a prefix replacement. And I want to make that, the reason I'm making that, writing that sentence all the way out is because, for instance, you also have the option of like flipping the two halves, and I'm not going to define that to be, that's not the action I'm talking about here. All right, but once you have an action or a partial action, you can start thinking about things like primitive and imprimitive partial actions. And so our starting point then is to look at, what imprimitive actions look like. Starting point. Restricting to imprimitive partial action. Okay, and so what that means for us, right, is that means it is going to be preserving some sort of notion of a block structure on here. And so what that means is it's going to be preserving, for instance, classes of vertices. And so what we can do to start thinking about these imprimitive actions is we can start coloring the vertices and then requiring, for instance, the elements that we consider to preserve the coloring. So for instance, I can color this. This coloring, you can just color however you want, and maybe you want to consider elements. So essentially what we're doing here is we're putting an equivalence relation on vertices, and what we can consider, so we can consider elements which preserve this equivalence relation. All right, but an arbitrary coloring of the tree is not one that's going to necessarily be compatible with this partial action of V. So we put a couple of restrictions on the types of colorings we're going to look at. All right, so we'll say coloring is coherent if whenever alpha is equivalent to beta, then alpha 0 is equivalent to beta 0, and alpha 1 is equivalent to beta 1. Right? I mean, this is just saying that if I add in this extra caret, like I'm still preserving, right, these equivalent relations. And likewise, we can talk about reduce, which is going in the other direction. So reduce means whenever alpha 0 is equivalent to beta 0, and alpha 1 is equivalent to beta 1, then alpha is equivalent to beta. Right, and again, this just says that these two properties are going to say that, you know, whether or not we preserve the coloring doesn't depend on our choice of representative of 3 pairs. So we'll call reduced and coherent coloring a type system. And again, the point is here is we're just making the obvious restrictions on these equivalence relations to make them compatible with, you know, working with different representatives. So whenever you have such a reduced and coherent coloring, then really like all you have to do is define what happens on a finite set of, or on a set of pairs. So, you know, you're always going to have your top vertex, which is kind of unique. But let's say the top vertex, we have red on one side and green on the other. And let's say we have a green vertex. And whenever I see a green vertex, I see 2 children which are red. And let's say when I see a red vertex, I see, I don't know, red and green. All right, so like a set of information like this is enough to tell me how to fully color my tree, right? So what it says, right, is at my first level, I see red and green, and then below green, I'm gonna see red, and below red, I see red and green. And we know what happens below green, we know what happens below red, right? And this lets us fill out the whole tree here. All right. So now then, yeah, so given such a relation like this, we can talk about the stabilizer then of the relation is going to be the set of elements G and V such that alpha G. So if alpha G equals beta, then what do I want to say? If alpha G equals beta G, then alpha is equivalent to beta for all the finitely many alpha and beta. All right, so all the finitely many, again, it's just because we have this partial action. Things are only defined partially. So in other words, what we're saying is if, you know, one red vertex gets mapped to another red vertex, all the red vertices get mapped to red. But if, you know, some of them get mapped to green, they all get mapped to green, right? It's just preserving this equivalence relation. Right. Yeah. Okay. So, yeah. So, okay. So whenever we have some proper type system, so lemma, then is that if an equivalence relation, you know, is a type system that's not universal, or trivial, then maybe not too surprisingly, the stabilizer of this equivalence relation is a proper subgroup of B. Right, there are elements of B that will not be in the stabilizer. But what we do here, though, you know, but the more general question, though, is when is it maximal, of course. All right, and so to answer this question, we first translate the statement to graph theory. And the way we do this is we take our type system on the tree and we quotient out by this equivalence relation. And what we're left with is a graph that then we can try and understand. All right, so example. All right, so for instance, take my tree and I'll color alternating levels red and alternating levels green. All right, so what we can do here then, yeah, the point is we're going to quotient out by this equivalence relation, and what this is going to leave us with, so we're always going to have this starting vertex, and then if I read a 0 or I read a 1, I always go to a red vertex. And then if I read a 0 or a 1, out of my red vertex, I go to a green vertex. And if I read a 0 or 1 out of my green vertex, it takes me back to red. Yeah. And this is what we'll call the type graph. All right, so this is like, you know, the subgroup here, the subgroup that stabilizes this is the one that preserves basically, you know, whether or not a vertex is on an even level or an odd level. Like this is the subgroup here. Okay, and so now at this point, you know, our question really becomes a graph theory question. And so what we tried to do is we tried to understand then first, you know, about type systems that don't have any proper quotients. So let's call a type system simple. If it's only proper quotient, proper type system quotient. Is the universal one. The universal relation. And so then what we saw, so theorem, all right, so our theorem was that if you have a finite simple type system, so given a finite simple type system, the type graph is one of the following. All right, so I'm not going to write super formal definitions, but we'll draw some pictures. So the first is something that we call nuclear. All right, so what nuclear means is, you know, you have your starting vertex, and after some finite amount of time, no matter what path you followed here, you end up in some strongly connected, inescapable piece. Unescapable. So we have this subgraph where you can get from any vertex to any other vertex, but you can never escape the subgraph, right? No matter, you know, following, because remember these graphs are directed, so we have directed paths there. So these will be like directed paths here. The second possibility that can occur so 2 is what we call binuclear. And so similarly, you have like, you know, these starting paths, but then after some finite amount of time, you end up in one of the 2 nucleuses. So you have possibly 2 nucleuses, but the 2 nucleuses both have just a single vertex in them. So you would have like a 0 edge here and a 1 edge here. So we have two unescapable subgraphs of size 1. So yeah, so if you have more than one nucleus, the point is this is the only possibility that can happen, because otherwise you'll be able to quotient it down and find a proper quotient. And 3 is what we call atomic quasi-nuclear. All right, so similarly, we have our starting vertex. You know, we have some finite amount of time before we end up in some strongly connected portion. But this time, the strongly connected portion is not necessarily inescapable. It can escape, but if it escapes, it only ever escapes through this one single vertex over here. And this vertex is unescapable. All right, so what I have here, my pieces, this is a strongly connected piece. And then we have an unescapable vertex here. Okay, and then, so once we have this classification, then we could go case by case, right? And try and understand whether these give maximal subgroups. And as it turns out, if you're in any of these 3 types, you indeed get a maximal subgroup of so going case by case, we get so let tilde be a simple type system. And in fact, here I'm making no assumption on finiteness, so this can be finite or infinite. That is one of these 3 types. Then the stabilizer in V of this equivalence relation is a maximal subgroup of V. All right, and so what this says to us, though, is it means, yeah, we have a full classification of what finite simple type systems are, right? And those will all give us these maximal subgroups. We also get some infinite type systems that give maximal subgroups. The infinite case is still a bit mysterious to us. It's a little bit harder to say what's happening in general. We don't have a full classification in that case. It is worth noting that there are lots of maximal subgroups that come up using some infinite type system. And an example of this is if you take some ray in your tree, so you take an irrational ray, and the tree, so meaning like there's no pattern that you're following, and you just want to stabilize this point in the boundary of your tree, then the type system that gives it to you is the one where you color everything on this ray with one color. Well, no, that's not right, right? So you're going to put some colors down this ray, right? You can't just color them all the same, but anyway, you color it, you know, and with different colors as you go down, but outside of this ray, you color everything the same. Red is everywhere outside that ray is a bunch of different colors, but what you get is you would get exactly this atomic quasi-nuclear thing, because the point is, as soon as you step off the ray, you're in a red vertex, right? This is where this atomic quasi-nuclear is coming from, is it's exactly things that look like ray stabilizers here, right? And since the ray is irrational, you need an infinite number of colors going down the ray. Okay, right. So this gives us a whole host of new maximal subgroups that, you know, we didn't know about before. And it is worth noting that one can distinguish isomorphism types of these things, because one of the steps along the group is setting up a semi-group that sort of captures the dynamics of the action, and using the Rubin's theorem. Rubin's theorem tells you about like the uniqueness of these types of actions. And so you can use Rubin's theorem to kind of distinguish whether or not two of these maximal subgroups are isomorphic. And we think this will actually, using infinite type systems, let us get uncountably many isomorphism classes of maximal subgroups.
So you describe some maximal subgroups, but you don't claim that we describe all of them.
We don't claim that we describe all of them. Indeed, we definitely know we're missing some. And yeah, and it's not at all clear what all of them will be, but we have some conjectures for what all of them should maybe be. We think most of them will be coming from these type systems, except for maybe, so one maximal subgroup that doesn't come from this type system is Thompson's group T. So Thompson's group T is maximal, but preserves no type system. And we don't know. Of course, you can take conjugates of T as well, but you know, to like basic things like taking automorphisms of V and looking at the image of T and under that morphism, it's not clear that there's anything besides that, and we sort of conjecture that maybe there's not just conjecture. And all a little evidence here, 7 or so minutes. Conjecture. We think maybe, you know, again, yeah, here I should say, to more things. This might be true. I mean, one is just that we tried really hard to find some others and failed miserably, and you know, over years of trying, like literally years. But the other is that, for instance, T. So T has, yeah, you can. Right, what do I want to say? So there is a primitive action of T on the set of pairs, primitive partial action. So if you look at pairs, alpha and beta, where alpha and beta are cones that are disjoint and don't union to the whole Cantor set. So if you look at sort of pairs of points, there's a partial action of T on the set that is primitive, that is imprimitive. It does preserve a block structure on this. But all of that needs, you know, defined because all we have here is partial action. So you have to make precise what you mean by, you know, imprimitive partial actions and this sort of thing. But indeed, so the point is, yeah, Thompson's group T does not act too transitively under this partial action. And in fact, we can prove that any subgroup that does that too transitively is all of V. So we spent some time trying to develop some techniques that let one determine whether or not you actually have a proper subgroup or not. Okay, so theorem. So let H be a subgroup of V whose partial action on the set alpha and beta defined exactly as above. So the component alpha union the component beta does not equal the whole Cantor set, and alpha and beta are incomparable in the tree. All right, so such that the partial action on the set is transitive, then H actually equals V. So we have, so as soon as right. So two transitive actions in some sense imply that in fact you get all of V. So T is something that is not too transitive, but as soon as you go to too transitive, you get all of V. And this theorem is reminiscent of a theorem from finite group theory. Well, not finite group theory, but from permutation groups. I shouldn't say finite group theory. So whenever you're studying Thompson group V, it's kind of a general motivating. There's a philosophy around V, which is that V is somewhat like a permutation group, right? You're not actually permuting things because there's some stretching and compressing going on as well. But behaviorally, it's often like analogous to a symmetric group. And there's a theorem due to Peter Cameron, which says that, some things about restrictions for how homogeneous and transitive actions can really be. So if you suppose that a group G has a highly homogeneous action on an infinite set omega, and that for some k, G is k transitive, but not k plus 1 transitive. And k is at most 3. And there exists a relation rho on the set, which is either a linear order or a circular order. Such that every element of G either preserves or reverses rho. So the point here is that the subgroup of Thompson's group V that preserves a circular order is T, right? Like that's how you characterize T. The subgroup that preserves a linear order is F. F is not going to be maximal because it's contained in T. But this theorem, kind of suggests to you that if you're looking for actions that are, where you have sort of this behavior of maybe not being highly homogeneous. Well, yeah, so when you're looking at these actions, right, the things that you might expect are things like circular orders and linear orders and this kind of thing. And I mean, we don't know, right? It's still pretty unclear what's happening in the infinite case. Whether, yeah, you have other types of type systems or, I don't know. Yeah, the point is where we don't have a classification. We would love to have one. I think we're pretty far away from having one at the moment. It would be great if this conjecture is true, but we don't know. All right, thank you.
So is there, like, given two subgroups as mean, is there some sufficient condition for the free product of those to embed the?
Okay, good question. I think probably, like, you can do a lot of like ping ponging things on the boundary, on the counter set. So there probably is some kind of ping pong condition. Yeah, but in general, I don't know. I mean, yeah, obviously it's not true in general that the Z squared free product Z doesn't embed, and obviously it's Z squared and Z. Yeah, so I don't know. It is true that the free product of any two finite groups embeds in V, so not just do all finite groups, but all their free products do as well. So every, but yeah. My guess is, I don't know one, but there, it would be surprising if there was.
I mean, finite is a condition.
Finite is a condition, yeah, finite is a condition. Yeah, but maybe, probably if you can like, maybe put it like in a, like, if you can put the subgroup so that its support is not full or something like that would be my guess. That might be kind of, or like overlap. Yeah, if you can find it so its support is not full, you can kind of put it wherever you want in the tree. And so then you could take your two copies and kind of overlap them just a little bit and then maybe do something fun or something like that. You know what I mean? That would make it nice. Thank you for doing that. Yeah.
And is it possible to describe homogeneous spaces in some human way?
Oh, right. So homogeneous, see if I remember these definitions. It's been a while since I've talked about this term. So homogeneous, so highly homogeneous. Right, so what we mean here is when we talk about two transitive, we talk about preserving the order on the ordered pairs. And when I say homogeneous, I don't care about the order on the pairs. So when I say highly homogeneous in this.
But not for Thompson groups.
Oh, in general, okay, yeah, I don't know. Yeah.
And what means words highly homogeneous?
Yeah, so what I mean by highly homogeneous is if you're transitive on orders, on sets instead of ordered pairs, right? For all K.
Okay.
That's what we mean by highly homogeneous.
Oh, but okay, so you have highly homogeneous things, but then they're not as soon as you add an order in because of things. That's
yeah, so this says if you have a highly homogeneous set, but that, so the restriction here is when you say there's some K for which it's K transitive, but not K plus one transitive.
Oh.
And that's what then forces the fact that you have some like bound. Yeah, and for us, the bound is 2, right, actually, right? 2 transitive means B. So you can find things that are 1 transitive but not 2 transitive. But in B, you cannot find things that are 2 transitive and not 3 transitive. It's the like way to convert that. But again, this, in our setting, it's a hard draft and a block.
Does this work for human Thompson groups?
Yeah, I think so. We wrote it just for V, but I think most of the ideas would work just fine if you change the degree of the tree.
Green Thompson, one square.
Brent Thompson might be harder. I don't know. Yeah, I don't know. I would have to. I have not tried, but yeah, I don't know if it works. Maybe.
I mean, I don't even know if we know something about maximal subgroups there.
Yeah. I mean, mostly there's some results about maximal subgroups of F. But even there's not many, right? Even though F is by far like the most studied of the 3 groups. Gilly Golan just put a paper on the archive actually super recently where she proved some kind of strong things about
What does she say?
so she, right, so what is it that she proved something about things called closed subgroups. And I don't know the definition exactly, but it's about, I think it's maybe related to these instructions, but I don't know enough yet to know. But
it's related to maximal sub.
but it's related to maximal subgroups, yeah, of that, yes, yeah. And so these closed subgroups are like these subgroups that are defined using automata, but all the elements only come from the automata or something like that. Like the closed means that, like, in fact, they can get all the things, but there's some kind of automata going on there that she talked about. And Tatiana Smirnova and Nagaveta and another author also had some work on F where they prove that's another variation on a Thompson group is a maximal subgroup of F. But that's more or less it, right? There's not a ton of stuff there. There's some earlier work by Gilly and Mark Sapir and stuff.
A very naive question or remark, since not surprisingly, but the question of amenability and unamenability of the group F was mentioned today. Also, speaking about subgroups, is it true that if suppose that the group F is non-amenable, is it true that if you look on its subgroup, there would be hardly any subgroup which could be non-amenable for different reasons of the group itself or something? So is it true that it's probably not helpful to look on subgroups, or is there any chance?
There's some statement about subgroups of F that it's like either every subgroup is, I want to say, solvable or contains
Yes,
F.
there are some claims.
Right, it's something like that. Every subgroup either contains F or it's solvable.
It contains F.
Yeah, that's the other. It's something like that. I forget what it, I might have the statement slightly wrong, but the point is, we're going to subgroups and for F. That's it. Yeah.
Even if it contains F, I don't believe it, but in principle, one could have a simpler reason maybe for some.
Yes, maybe.
To be
Yes.
honest.
Right. That's right. Yeah.
Let's thank all the speakers for that. Today it was unusual day, right? We are returning to usual Tuesdays.
At least a few of us will go to dinner if anyone wants to join for dinner.